Hey everybody, so one more topic about fluid mechanics. Let's talk about buoyancy. So let me just state Archimedes Principle. So basically, let's say you have a tank of water. Okay, and then you have some object submerged in water, like a block. So the buoyant force is the weight of the displaced fluid. That's Archimedes' principle. Okay, so maybe just think about that. The buoyant force, so it's a force, equals the weight is a force, right, of the displaced fluid. Right, so imagine there's this block, let's say a block of wood or something. How much water is this block displacing? So let's say this is the volume is 1 cubic meter. Right? It's displacing 1 cubic meter of water. If you were to weigh 1 cubic meter of water, like how much does that weigh? Something newtons. That amount of force is the buoyant force acting upwards. So the buoyant force. Right? If you take the mass of that block times g, that would be the weight. Okay, think about this scenario. Now let's change it a little bit. Let's say the block, so here's a surface of water. Let's say the block is floating like this. Let's say halfway in the water, halfway out of the water. And then it's 1 cubic meter. So now, how much fluid is the block displacing? Right? If it's 1 cubic meter and it's like halfway in the water, halfway out of the water, then it's displacing half a cubic meter. Right? So then how do you compute the buoyant force in this case? It's the weight of the displaced fluid, so which is like the weight of the water that's displaced. What mass of water is displaced? Remember, density is like mass per volume. So mass is like density times volume. But then this would be the volume of the displaced water fluid. Right, so then, in this case, that would be half a cubic meter, and then this would be the density of the water, right, in this tank. So let's give an example. Let's say I didn't know it was halfway floating in and out of the water. So different example, like there's an iceberg. Okay, so how much of the iceberg is above the water? How much is below the water? And let's say we know the density of the ice, and we know the density of the water. And then I'll just call this height above and height below. Okay, so what is the free body diagram look like? Right, here's your block of ice, your iceberg, there's force upwards, which is buoyant force, downwards, which is the weight, and then that's it. So some forces in y, buoyant force minus weight equals mass times acceleration. Okay, so I mean, this could be accelerating, but let's say for this example, it's just sitting there static, so the acceleration is 0. What's the buoyant force? It's the weight of the displaced fluid. So density of, let's say, water, the volume of the water that's displaced, g, right? So this is buoyancy. And then the weight, mg. But this is for the ice, right? So this is the mass of the ice, which is density of ice, volume of the ice, G. Oh, sorry, this should be a minus sign. Okay. Equals mass times acceleration, which in this example is 0. All right, now then we just need to know the volume of the water, the volume of the ice. Okay, so then let me just rearrange this a little bit. So this factors out. I mean, we can divide by something non-zero. So the volume of the water, as our density of the water, volume of the water equals density of the ice, volume of the ice. So like we could rearrange this in any way, but just let's see. We could maybe phrase it like this. The volume of the water is the volume of the ice that's below the surface, right? And then the volume of the ice is actually the total. So if I just like move things around a little bit, I'll move this over here. And then I'll move this over here. Then look at what just happened here. If we know the density of the ice, I'll just make up a number, like it's 0.9. Sorry, 900. And density of water, 1,000. I just made these numbers up. I mean, it's close, but right then, that's about 90%. So then look, that means about 90% of the iceberg is below the surface of the water, 10% is above. And that'll just change based on these densities. Okay, so try this example for yourself to see if it makes sense to you. And then maybe for practice, what if you have the tank of water and you had some ice cube maybe, or a block of ice connected by a string to the bottom of this tank. And we know the density of this ice. Could you solve for the tension in the string? What would the free body diagram look like? There's buoyancy going up. The ice itself has weight, and there would be tension in the string. Right? And then when you cut the string, what would happen? The free body diagram would just look like this, no more string. And if this force is larger than this force, it would accelerate upwards. If this force is larger than this force, then it would accelerate downwards. And then if this force is equal to this force, the acceleration would be 0. That doesn't really tell us anything about the velocity. The velocity could be constant. Okay, so try some of this to see if it makes sense, and just remember the general definition right here. Buoyant force is the weight of the displaced fluid. Okay, let me know if you have other questions. See you in the next video.